everybody, it's PChem Help. This is John. Today, first order kinetics. That is, a reaction where the rate depends linearly on the amount of reactant that you have. That's about it. Let's go to the digital whiteboard and get started. So consider the simple classic chemical reaction, where we have reactants going on to form products in a 1-to-1 stoichiometric ratio. And let's focus on the rate at which this happens, where the rate is the rate how fast product is being formed. So it's the rate or the change in product and the change in time. Or we could focus on the loss of reactant in time. So the rate is expressed as the change in concentration with time. It is the speed of the reaction, hence v for velocity. Exactly like the speed of your car is the change in distance traveled divided by the time spent traveling. The speed of the reaction is the change in concentration divided by the time the reaction has been going on. To relate back to speed and your car again, the speed shown in your speedometer is your instantaneous speed, the derivative. And your average speed over some real period of time is delta x over delta t. We're going to be looking at instantaneous changes and derivatives. So in our simple first order reaction, reactant R turns into product P. And we can look at some graphs. Imagine you had a way of measuring the amount of reactant you have in your solution or equation or whatever it is. So if it's a first order reaction, you'll see a line like this. Okay? And if you can also measure your products, you'll see a line grow in and level off like this. So we said that the rate of this reaction depends linearly on the amount of R that you have. And notice here that when R is larger, we have a steeper slope here than when R is shorter, we have a more shallower slope. And the slope here is the derivative of this line, which we've already said is the rate. Okay? So the rate is proportional to the amount of reactant we have, and the proportionality constant is K, which is known as the rate constant. This equation is known as the rate law, and this is a first order reaction because the rate depends on R in a linear fashion. That is, on R to the power of 1, to the first order. So the loss of R will be exactly equal to the gain of P. So we can write this again. But we also know that V is equal to KR. So we can rearrange a bit and get all of the R terms together. And let's just say dr dt is minus K, the concentration of R. And rearranging now, we get this. We get the concentration as a function of time, which is usually what we want. We will need to integrate this equation. And by integrating, we will get a function R as a function of t. That is read R of t. So let's integrate, and we'll say at time 0, we have R naught, and at time t, we have some amount R. Now these are both integrals that you should know, you should be very familiar with. The second one on the right is trivial, it's very easy. And the first one you will see again and again, so you need to remember it. So solving these integrals, we get the result that the natural log of R over R naught is minus KT. We can take the exponent, or exponentiate both sides, multiply by R naught to get R is equal to R naught e to the minus kt. And this is the integrated rate law. We have R as a function of time. Now, we are also interested in how much product we have, and we can manipulate this equation to get the concentration of P as a function of time. We need to make use of another equation, that the total sum of P plus R has to equal R naught plus P naught, right? The amounts that we started with. This is simply the conservation of mass. Now, if we say that we are starting with only reactants and that P naught is 0, then we can rewrite R in terms of P. We get that R is equal to R naught minus P. So now substituting that into the left side before, get this equation. And we can solve this for P, where the concentration of P is equal to R naught times 1 minus e to the minus kt. And now we have P of t, where we have exponential growth, whereas for R we had exponential decay. We really like linear equations in science, which I think stems from having to do every calculation and every plot and everything by hand back in the day without computers. So we like to linearize these equations. We want to linearize the reacting equation as a function of time. We can just go back to the natural log we started with, and we get natural log of R equals minus kt plus natural log of R naught. So, if you plot natural log of R versus t, we should see a line with a slope of minus k and a y-intercept natural log of R naught. Okay, only one more thing about these first-order reactions. Sometimes we're interested in how long it takes for half of the reactants to go away. This is well named the half-life. So we can go back to our integrated rate law, where we have R is equal to R naught e to the minus kt. And now we are interested in the time when R is equal to R naught over 2, 1/2 of what we started with. And at this time, we're going to call it T 1/2. This is the half-life. So now we can write R naught over 2 is equal to R naught e to the minus k T 1/2, and we will be solving for this time, this half-life. We can take the inverse. First, let's cancel out R naught. So we just get 1/2 is equal to e to the minus kt 1/2. We can take the inverse of both sides and then exponentiate to get the natural log of 2 equals kt 1/2. And solving for t 1/2, we get that equal to the natural log of 2 over k. So this is actually pretty interesting. The half-life is independent of the concentration that we started with, or the concentration that you have. At any point in time, for a first-order reaction, it'll take the same amount of time to lose half of your reactants, no matter how much you start with. If you go back to a plot, like so, we can just do this kind of by hand here. If I take about half of what I started with, I get to this first time. If I take half of that again, I get to my second time. If I take half of that again, I get to another time. And it looks like I did actually draw this correctly here, which is nice. These are all evenly spaced. Okay. So the half-life is consistent, and it only depends on K. Okay, there you have it. Let's call it a day. First order kinetics.